I am Professor Srimati Joshi Shubhada Ramesh, working in Srimati Pushpa Tahire Mahila Mahavidyalay, Malegaon camp. Now I prepared the e-content for T.Y.B.Sc, paper number 5 and 6, ordinary differential equation. Now previously in the first and the second chapter, we discussed the linear differential equation with constant coefficient. Now there we discuss so many methods that how to solve the linear differential equation with constant coefficient. Now in the first chapter we discuss how to find the complementary function, then how to find the particular integral. Now in the second chapter we solve the non-homogeneous linear differential equation with constant coefficient. In that we consider the various methods such as method of undetermined coefficient, method of reduction of order, method of variation of parameter and so on. So now here I am prepared e-content for chapter number 3, the power series solution. Now here we consider how we solve the linear differential equation by using the power series solution. So first of all we consider the linear equation and the power series. Now here as you seen we consider the linear homogeneous differential equation of second order, namely b0x y double dash plus b1x into y dash plus b2x into y equal to 0, that I denote by 1. Now then as b0 of x not equal to 0, so we divide equation 1 by b0 of x, then we obtain equation second. Now again we denote that rational coefficients b1 of x upon b0 of x is equals to p of x, and b2 of x upon b0 of x is equals to q of x. So equation 2 can be written as y double dash plus p of x into y dash plus q of x into y is equals to 0. So where p of x and q of x are the rational function of x with denominators that do not vanish at x equal to 0. And then we assign the solution for equation 3. So that we discuss here. Now then first we consider y is equals to y of x is the solution. Then from that we find y dash, we find y double dash, we find y triple dash and so on. So we continue this process and then by using the Maclaurin's formula we write y of x is equals to y0 plus summation n equal to 1 to infinity y raised to n of 0 x raised to n upon n factorial as a solution of equation 2. Now then as we already discussed in real analysis the concept of convergence. So here we consider the convergence of power series. Now we know that the power series summation n is equals to 0 to infinity an x raised to n converges either at x equal to 0 only for all finite x, or the series converges in an interval minus r less than x less than r and diverges outside the interval. So here we consider the series, then we differentiate that. Similarly when we integrate we write in this form, and then we conclude the series is term-wise differentiable and integrable. The series of derivatives of the separate terms converges to the derivative of the sum of the original series. So note that the interval of convergence remains unchanged. Then we discuss what is the ordinary points and the singular points. So for a linear differential equation which is mentioned in equation 1 with a polynomial coefficient, so the point x equal to x0 is called an ordinary point of equation 1 if the coefficient of the highest order derivative, that is b0 of x that not equal to 0 at a point x0. Then the singular point of equation 1 is any point x is equals to x1 for which b0 of x1 equal to 0. So we shall obtain the power series solution valid near an ordinary point of linear equation. Now here I given some examples on singular point, that how we calculate the singular point. So we concentrate on first example. For each equation, list all the singular points in the finite plane. The equation is x y double dash plus y dash plus xy is equals to 0. Now see here the equation is of second order derivative, that is y double dash is here. Now coefficient of y double dash is x, that is our b0 of x is equals to x. So this equation has singular point at x equal to 0. Now we consider the second example, y double dash plus 2xy dash plus y equal to 0. Now see here b0 of x is equals to 1 and we cannot write 1 equal to 0. So this equation has no singular point.